All right, so in this video, we're just going to go through a few different practice problems, and then the way it's going to be set up is I'll have the question on one slide, so you may want to pause it after the question appears, because then I'm just going to move to the next slide, which is going to show the setup and then ultimately the solution. Like I said, with each of these different slides, when the questions appear, if you want to just kind of pause it, give yourself a chance to work through it. And then I'll go through it in the next slide so you can check your answers and everything. But with this first one, we've got two different questions, both looking at the same thing. We want to identify which of these options is representing a buffer system or buffer solution. And with that, we just want to remember that a buffer solution is going to be a solution that contains a weak conjugate acid and base. So if we look at the options here, if we look at the first one, phosphoric acid, and then we've got it with, what would this be? Potassium dihydrogen phosphate, maybe. I forget the exact name for the H2PO4 anion. But what we're going to see here is the phosphoric acid is going to be a weak acid, and then the anion, the H2PO4 minus, is going to be its conjugate base. So that's going to be an example of a buffer system. With the next one, we've got water with sodium hydroxide. So since sodium hydroxide is going to be our strong base, this is just going to be a regular basic solution. The next one, we have hydrochloric acid, and then we would have the conjugate base. We'd have that Cl minus with it. But since hydrochloric acid is a strong acid, the chloride ion and the hydrochloric acid really just aren't going to make a buffer solution. It's just going to be an acidic solution, since neither of these ions are going to be acidic or basic when we're looking at the sodium, the chloride. With the next one, that's just an acid and a base, strong acid, strong base. So it would just, if we had equal amounts, just be water. Or if we had more of one than the other, it would just be acidic or basic, depending on which one we have extra of. And then with the final one, that would just be a neutral solution, because none of these ions are going to affect the pH. So we wouldn't have the buffer, we wouldn't have the weak acid conjugate base in that case. And then looking at the second one of those options is the exact same, so HCl, NaCl, or NaOH rather. The fourth one here is the same as the first one. And then the third option of that first question is pretty much the same as the third option here. It's just we're replacing sodium with potassium, but we're going to see the same thing, strong acid with just a neutral salt. So we're not going to form the buffer solution. And then with the final one, ammonia with water is just going to give us a basic solution. But what we're going to see with the second option here, ammonia with the ammonium chloride, ammonia is going to be our weak base. The ammonium ion is going to be our conjugate acid. So we're going to see that'll be our buffer solution there. So again, with it, we want the conjugate acid with the conjugate base, and we want weak acid, weak base. And that's why these buffer solutions are going to be fairly resistant to pH change. They've got the conjugate acid, they've got the conjugate base present, so it can accept acid or base and then neutralize it, at least up to a point. We've got that buffering capacity, can't take an unlimited amount. But for a little bit at least, it's going to be able to accept the acid or the base that's added without changing the pH drastically. And then, like I said, with it, we've got those two as our buffer solutions. All right, so for the next one then, we've got two different questions, and they're going to be similar. So calculate the pH of a buffer solution that is 0.105 molar sodium bicarbonate, and then 0.125 sodium carbonate. And then for the second one, we want to do a similar thing, figure out the pH of a solution that's formed by mixing those two together. So we've got 65 milliliters of a 0.2 molar sodium bicarbonate with 75 milliliters of a 0.15 molar. And then with this one, remember, just to get started, this is going to be looking at the Henderson-Hasselbalch equation. So we've got pH is equal to pKa plus the log of the base over the acid. These are going to be the concentrations. So with that final piece, base over acid, sometimes we also write it as A minus just over HA. But with it, remember that P is just representing the negative log. So we've got the Ka for the bicarbonate ion, so we can get the pKa. We've got the concentration, at least for the first one, of those conjugate acid, conjugate base. We just have to think about which is going to be which. And what we're going to see is that bicarbonate ion is going to be A minus, HA, or HA, excuse me. And then just the carbonate is going to be A minus. So we can take the Ka, take the negative log of it to get pKa, and then we can plug in these concentrations. Since we're going to get one carbonate for every one sodium carbonate molecule, we're going to get one bicarbonate for every one sodium bicarbonate. We can just take these concentrations and plug them in. We'll have 0.125 on top because that's going to be the concentration of our base. We're going to have 0.105 on the bottom because that'll be the concentration of our acid. And then with this one, when we go through and actually do plug it in, like I said, we can just assume these concentrations are going to be the concentration there for those individual ions. So when we take the negative log of that Ka, we're going to get 10.25. And then with the so with this, let's just change this quickly. So this piece, we're going to get rid of that. So it really should be 0.076. So when we take the log of those concentrations, we'll get 0.076. So when we add it, what we're going to see is the new pH will be 0.033, 10.33, excuse me. So with this, I just found this set up online, this picture at least, just so I didn't have to put it in. But it does look like the final answer there is just a little bit off. And with it, we're going to get 10.33 in this case. And then for the second one, we go back for a second. If we go back for a second, this one's going to be very similar. It's just in this case, we're mixing two solutions. So we've got to do M1V1 is equal to M2V2 to figure out what those new concentrations are. Or what we can really do is just focus on how many moles we're going to have in each of those. Because if you think about the setup we have at the top here, molarity times volume, that would be M1V1 for each of these solutions. But in both cases, M2 is going to be the same. So if we divide both of these moles by the same volume to get the new molarity when they're fully mixed, it's going to be the same ratio as what we see here. So we can actually just take these moles and just plug them into the equation itself. But we still have the Ka, so we can still get that pKa, and it's going to be the same because it's still the bicarbonate that we're looking at for the acid. And with this, oops. So what we're going to see is we'll have 10.25 for that pKa plus negative 0.06. So what we'll see is we'll get a new pH of 10.19. And again, the setup is correct. This number doesn't seem to be correct, at least for what I'm getting when I plug it in. Yeah. So I'm getting 10.19 as the pH for this one. And again, the reason we can just take these mole values and plug them in is just because the volume is going to be the same since we're mixing them in the same solution. So we'll still have it in the same ratio. Okay. And then for the next one, what ratio of concentrations of sodium acetate and acetic acid would yield a buffer solution with pH of 4.5? And then it gives us the Ka. So in this case, if we think about it, pH is equal to pKa plus the log of the base over the acid. We've already got the pH, we've already got the Ka. We could get the pKa. So when we're looking at our equation, if we go back here, we've got this equation. We've already got that term. We can get this term. We're looking for this ratio of base to acid. So what we're going to do when we plug it in is just look at those different values. So we'll have 4.5 negative log of that Ka. So we get 4.74 there. And then when we go through and actually go through and solve for this ratio now, because we're not going to have the specific concentration. If we knew what one of those concentrations were, we could use the ratio to figure out what the other concentration is going to be. But in this case, we're just looking at the general ratio. So we can kind of just treat this A minus over HA. We can just kind of treat that as X. That entire thing is X. So when we go through, we'll get negative 0.26. It should be negative 0.24. Let's see. So that should be 2.4, which is that, and to the negative 2, which doesn't actually change that number at all. So in this case, what we're seeing is 0.58 when we solve for this entire thing. So if we think about the ratio, then that means for every 1 HA, we're going to have 0.58 for the concentration of A minus. So if the concentration of HA had been 0.01, then the concentration of A minus would be 0.0058. But without knowing the actual concentration of one of these pieces, we can't solve for the concentration of the other. We can just figure out what that ratio is going to be. So in this case, it's just using that Henderson-Hasselbalch equation just to solve for the ratio here rather than the actual pH. So we had both of these already. So we're just looking at solving for a different portion of that equation. So see if you can do the same thing. But in this case, we're looking at and actually for this one. Yeah. So for this one, we're actually looking at a base. So it's going to be a slightly different equation in this case. So if you think about it, we've got POH here. We won't have pKa. We're going to have pKb, which means we're just going to flip the final piece of this. In this case, we'll have acid over base. And then for this one, the base is going to be ammonia. We've got the Kb for ammonia. So the acid is going to be that ammonium chloride. But with it, we want to figure out what ratio of the concentration of those would yield a buffer solution with a pH of 5. So we've got that piece. We can get that piece just by taking the negative log here. So again, we're looking for the ratio of those two together. With this one. Yep. So if we look at this one, like I said, we already had the POH 5. we've got the KB, so we can get the PKB still by just taking the negative log there. So we'll see 4.74. So when we combine those two, we'll get positive 0.26. And then, like I said, in this case, since we've got the POH and the PKB, we're going to have acid over base. So that's why we've got the ammonium ion on top. That's going to be able to donate a proton. So that's why it's going to be the acid. The ammonia is going to then be the base. So when we look at solving for it now, it's going to be that same idea. We can essentially just treat that entire ratio just as one variable. So we'll get 0.26 is equal to the log of those two ions, the ratio of those two ions. So if we raise both sides to the power of 10, we get 10 to the 0.26, 10 to the log of this, which is just going to then give us the ammonium over ammonia. So we'll see we're going to have a ratio of 1.8 in this case. And with this one, that means we're going to have more of the ammonium than we will the ammonia. So the other one was 0.58, meaning we had more of the denominator. But in this case, since we've got a number greater than 1, we're going to have more of the numerator. Yeah, and then with the next one, we're looking at different titration curves. And we've got different descriptions for what these acids and bases could be. So not specific, but just strong acid, weak acid, strong base, weak base, polyprotic acid. We could have different combinations of those types of solutions. And then depending on exactly what we have, we see different shapes to these curves. So if we're trying to identify which each of these are going to be, what are we adding to what? We can first just look to see where that pH is, to see what we have in solution. So in the case of this first one, we're starting with a low pH, so we're going to be adding base to acid. So if we look at the options here, we can eliminate A for the first one, because in that case, we're adding the acid to the base, so we'd start with the high pH. So what we're going to see is that second one will actually be the strong acid, a strong base. And that's why you'd see that also finishes low, has the equivalence point right in the middle, because it's going to be strong acid and strong base. With the first one, though, it's just kind of reverse. So we want to look for strong base being added to strong acid, which is going to be C. And then with the third one now, we're finishing at a higher pH, so we're still adding base. But in this case, we're starting at a higher pH as well. So we're going to have a weak acid. It's going to be B for this one, strong base added to weak acid. And then for the final one, we see multiple equivalence points, because and we're starting low, finishing high, so it's still adding base to acid. But since we've got multiple of these equivalence points, that's just going to be representing the polyprotic acid. So we would just have D for that. Okay, and then for the next one, now we're looking at the solubility product. We're thinking about precipitate formation. So we've got a solution that contains 0.01 molar silver ions, 0.02 molar lead 2 ions, and we're going to be adding chloride ions to this solution. Excuse me, losing my voice a little. And when we do that, there's going to be the possibility for silver chloride to precipitate, so AgCl. As well as the lead 2 chloride, so PbCl2. We want to figure out in both cases, what does the concentration of that chloride ion have to get to in order for a precipitate to start forming for both of these substances. And then using that information, we want to identify which of these solutions is going to precipitate first. So with both of them, we want to think about what is the solubility product expression going to look like. And for silver chloride, it's going to be relatively straightforward because we just have one of each of those ions. So it'll just be the concentration of silver plus the concentration of chlorine, or times the concentration of chlorine, excuse me. While at the lead 2 chloride, now we get 2 of those chloride ions per molecule. So when we look at the solubility product expression here, it's going to be the concentration of lead times the concentration of chloride, but we're going to square that chloride concentration because now we've got a coefficient of 2. But in each case, we've got the KSP already. We've got the concentration of those lead ions. So we can just solve for the concentration of the metal ions because one of them's silver. But we can use that information to then just solve for the chloride ion concentration, figure out what concentration does that have to get to in order for these precipitates to start forming. And for the silver chloride, like I said, since it's just going to be silver times chloride, we can just have KSP is equal to that silver concentration, solve for X. And we're going to see that the X in this case is going to be 1.8 times 10 to the negative 8th. So that's going to be the concentration of that chloride ion we need for precipitation to occur, at least for the silver chloride. Whereas the lead 2 chloride, now we've got chloride concentration squared. So we've got that KSP is equal to 0.02 times X squared. So when we actually go through in this case and solve for X, we're going to see 0.2 or 2.9 times 10 to the negative second molar for that chloride ion. And since this is going to be a higher concentration, we need more of that chloride ion in order for the lead substance to precipitate out. So we're just going to see the silver chloride would precipitate first in that case. And again, with it in each of these cases for the top line with this calculation, that's just the equilibrium expression. So KSP on the left, initial concentration of that metal, and then the X is solving for the chloride ion. It's just in this case for PbCl2, we've got that concentration of chloride squared, just because we get 2 of those chloride ions per molecule. Okay, and then this might be the last one. Yeah, so this is going to be the last one for this review video. But in this case, we're looking at the substance in enamel that helps to protect the teeth. So we've got hydroxyapatite. And then it's got the formula there. I've given you the molar mass just to save you a step. And then with the KSP, going to be 6.8 times 10 to the negative 27. But with that substance, when it can kind of react with acid to ultimately give the cavity. But what we can do is replace that OH with a fluoride ion. And what we're going to see is that's going to make this KSP even smaller, just because fluoride is going to be a weaker base than the hydroxide. So it's just going to give us even less of that substance dissolving. So if you think about the teeth, if we've got less of it dissolving, that tooth is going to remain stronger. So that's why fluoride can help protect teeth and reduce cavities. But with it, in this case, we want to use this information. We want to use these KSPs to determine what the solubility for each of these is going to be in grams per liter. So with this, in each case, we're going to want to kind of think about the way that they would dissociate. So what we're going to see with the hydroxyapatite, kind of just think about it's going to lose the hydroxide. The rest of this will be +1. Similar with the fluorapatite, we're going to lose that negative fluoride and then just have the rest of it be +1. So in each case, we've got a very similar dissociation reaction. But we've got drastically different KSP values. So we're going to wind up with very different solubilities. And then with it, let's go to the next, whoops. So with it, I'm using X for the hydroxyapatite, Z for the fluorinated one. So if we look here, for the hydroxy one, it's going to be X squared, because like I said, we're just going to get that formula, and then the OH is just going to separate, so we'll have positive and negative for the ions, but it's going to be 1 to 1. So that's why we've got X squared. And then when we go through and solve for X, because it's going to be that 10 to the negative 27th, we're going to see we get negative 14th for the exponent. And this is going to be the molar solubility. So this is moles per liter, remember? So what we can do is use the molar mass, which I gave you on the previous one, is going to be 502 for this substance. So we can just take this molar solubility and multiply it by that molar mass, multiply it by 502. And if we look at the units, mole per liter is what this capital M stands for. If we multiply by the molar mass, we've got grams per mole. So in this case, we got moles on top, moles on the bottom. Those are going to cancel. We'll just be left with grams on top, liters on the bottom. That's going to be the unit we want for solubility. Oops, and I messed that up. So this should be grams per liter as well. So for the original substance, we see a solubility of 4.1 times 10 to the negative 11th grams per liter. So a very, very small number. But with the second one, because now that KSP is going to be 10 to the negative 60th rather than 10 to the negative 27, we see the molar solubility is now 10 to the negative 30th. So it's much, much smaller. In this case, 16 orders of magnitude, or 15 really. But 15 orders of magnitude less. And then we see with the grams per liter, again, we're just multiplying by the molar mass so we get those units. In this case, we've got a slightly different molar mass of 504 because we've substituted that oxygen and hydrogen for a fluorine. But essentially the same thing. And in this case, we get the grams per liter, or the solubility in grams per liter to be 5 times 10 to the negative 28th. So if you think about it, we're going to have much less of this substance be soluble. And that's why it's going to help protect the teeth more than we see with the original substance there. But with this stuff, if you do have questions on any of this, let me know. And then related to this, there is the Chapter 17 practice on Canvas. So these notes are up there as well. But there is just the practice document that has different similar questions along with the answer key. So if you work through that and have any questions or have any remaining questions from any of these ones or anything in the textbook that you may look at, let me know. We can go over those as well.